uh, very, very fine-grained as you get close to it. It's almost like a powder. Ground mass is very fine. I'm going to step off the limb. That's one small step for man, one giant leap for mankind.
Good morning, good afternoon, and good evening to everyone who joins us from around the world. Welcome to the Stack Series podcast. We're so glad you're here. I'm Andrew.
And I'm Renee.
Today, we are exploring the current status of dark matter and dark energy. So, I was walking into the studio today, and I had this kind of weird moment. I was just standing on the corner, waiting for the light, looking at everything, the whole scene.
Yeah.
Glass buildings, cars, people on their phones, all of it.
Yeah.
And it all feels so solid.
It feels substantial, like this is it. This is reality.
Exactly. It feels like the whole story.
Yeah.
And then I started thinking about all the research we have for today, and this analogy popped into my head. I want to run it by you.
Okay, I'm listening.
Imagine you're standing in front of this massive, sprawling estate. I mean, a mansion the size of a city block. It's got everything. But for some, bizarre reason, the only thing you can actually see is the brass doorknob on the front door.
Just the doorknob.
Just a single floating piece of brass. You can't see the building, the roof, the foundation, nothing inside. Just this little shiny knob hanging in space. And if you had to describe reality based only on that, you'd say, well, the universe is a small, shiny brass lump. And you'd be so wrong.
That is a terrifyingly accurate metaphor for where we are in cosmology right now. It really, really captures the problem.
It sounds completely ridiculous when you say it out loud, right?
Yeah.
To think we could miss the entire house for the doorknob, but that's basically where we are with the universe.
That is exactly where we are. And it's probably the biggest lesson in humility that science has ever given us. Because everything we can see, everything we can touch or interact with, every single star, every galaxy, this microphone, the coffee in your hand, even the neurons firing in our brains. Astrophysicists call that baryonic matter.
The normal stuff.
Ordinary matter, the things on the periodic table. Protons, neutrons, electrons.
Right.
And when you actually do the math, when you put the entire universe on a scale, all of that, all of it, makes up only about 5% of everything.
5%. Let that sink in for a second. 95% of reality is just invisible to us.
We're the anomaly. We are just the froth on top of a very, very deep, dark ocean. The universe isn't a story about us. It's a story about this dark sector.
It totally reframes your whole place in the cosmos. You think you're the main course, but you're not even the garnish. You're just like the thinnest layer of dust on a massive invisible cake we didn't even know existed.
And for pretty much all of human history, we thought the dust was the whole cake.
So that's our mission today. We are going to dive deep into that invisible 95%. We're unpacking the dark sector. We've got the 27% that is dark matter, which we can sort of think of as the cosmic glue.
The scaffolding.
And the 68% that is dark energy, the cosmic pusher, the thing tearing it all apart.
And we are doing this at the perfect time. If we'd done this deep dive even a year ago, it would be a very different conversation. But the data that's come out in late 2025 and really January 2026 has just shifted the entire landscape.
There are some explosive new findings, especially about dark energy, that suggest the universe might not be behaving the way we've thought for the last 30 years. The plot is twisting as we speak. So, all right, let's start with the glue. Let's tackle that 27%, dark matter.
Let's do it.
Okay, first thing I want to clear up, because I think the name itself is a little confusing.
Yeah.
When we say dark matter, we don't just mean it's like in a shadow.
Right. Dark is a bit of a bad name, actually. A better term would be transparent matter or invisible matter.
Okay.
Think about it this way. If you have a dark rock in a room and you shine a flashlight on it, the light hits it and bounces back. You see the rock.
Light interacts with it.
Exactly. Dark matter doesn't do that. It doesn't reflect light, it doesn't absorb light, it doesn't emit light. It is completely, totally invisible to the entire electromagnetic spectrum. You could have a clump of it the size of a planet right in front of you, shine the most powerful laser in existence at it.
And the beam would just go right through.
As if nothing was there. It interacts with light about as much as a ghost interacts with a wall.
So if it's invisible and we can't touch it and we can't take a picture of it, how on earth do we know it's there? How do we know we aren't just making up 27% of the universe to make our equations work?
Gravity. That's the one thing it can't hide from.
Ah,
Dark matter has mass. A lot of it. And because it has mass, it pulls on things. It's like a poltergeist in a horror movie. You can't see the ghost, but you can see the chair sliding across the floor.
And the chair is the visible galaxy.
The chair is the visible galaxy. We see the stuff, we can see the stars, the gas moving in ways that only make sense if there is a gigantic invisible weight pulling on it all.
I love that. Okay, so let's talk about the detectives who first noticed the chair moving. This isn't a new idea, is it? We have to go back a ways.
We do. We have to rewind all the way to the 1930s. To a Swiss astronomer named Fritz Zwicky. Now, Zwicky was a brilliant guy, but he was also quite a character.
It's a bit of a personality.
To put it mildly, he was famous for calling his colleagues spherical bastards.
Spherical bastards.
He said they were bastards no matter which way you looked at them.
Okay, so maybe not the most popular guy at the faculty Christmas party, but definitely a sharp mind.
Incredibly sharp. And he was observing the Coma cluster, which is this huge beehive of over 1,000 galaxies, all held together by their mutual gravity. And Zwicky was measuring how fast those galaxies were zipping around inside the cluster.
I mean, what was he expecting to find?
Well, gravity holds it all together. And the gravity comes from the mass you can see the stars. So you add up all the stars, you figure out the total gravity, and that tells you the speed limit.
Like a car taking a corner. If you go too fast, you fly off the road.
Exactly. And Zwicky found the galaxies were moving at insane speeds, just tearing through space. According to the visible matter, the cluster should have just flown apart billions of years ago. The galaxies should have been flung out into deep space.
So the car should have flown off the road.
It wasn't even close. Zwicky did the math and realized that to keep those galaxies bound together at those speeds, there had to be hundreds of times more mass than what he could see in his telescope. He called this missing stuff dunkel materie.
Dark matter.
Dark matter. And of course, the scientific community pretty much ignored him for decades.
Why? It sounds pretty convincing.
It just sounded like a fudge factor. Like, oh, the math doesn't work, so let's just invent some invisible stuff.
It wasn't until the 1970s that the evidence became absolutely undeniable, thanks to an astronomer named Vera Rubin.
Right, Vera Rubin. And she was looking at individual spiral galaxies, things closer to home.
She was. She was looking at how they rotate. Now think about our solar system. The sun is in the middle, and it has almost all the mass.
Right, it's the big, heavy thing.
So Mercury, which is really close, has to orbit incredibly fast to not fall in. Neptune, way out on the edge, orbits very slowly. That's just basic gravity. Speed should drop off the farther you get from the center.
That makes perfect sense. And Rubin expected galaxies to work the same way. They have a bright, dense center full of stars. That's where the mass should be. The edges are all wispy and thin. So stars at the edge should be moving much, much slower than stars near the core.
But they weren't.
Not at all. It was a complete shock. She found that the stars at the very, very edge of the galaxy were moving just as fast, sometimes even faster than the stars near the center. The rotation curves, as we call them, were flat.
So it's like a merry-go-round. If you spin it really fast, the kids on the outside should be flung off.
They absolutely should be, unless there's something else holding them on. Rubin realized the only explanation was that the visible galaxy, the pretty spiral we see in pictures, is just the tip of the iceberg. It's embedded in a massive, invisible sphere, a halo of this other matter.
So the galaxy we see is just the shiny part in the middle of a huge, invisible structure.
That's the scaffolding analogy. Dark matter built the structure first, and then the normal matter fell into it and lit up. Without that dark matter glue, the Milky Way would have torn itself apart. We wouldn't be here.
That's a pretty unsettling thought. That our entire galaxy is basically being held together by a ghost.
It is. And since Rubin, we've found even more evidence. We can actually see it using something called gravitational lensing.
Okay, this is pure Einstein, right?
Pure Einstein. His theory of general relativity tells us that anything with mass bends space-time. So if you have a huge clump of dark matter, it acts like a lens in space. It bends and magnifies the light from more distant galaxies that are sitting behind it.
Can you give me a visual for that?
Yeah, imagine looking at a patterned tablecloth through the base of a wine glass. The pattern gets all swirly and distorted around the base, right?
Right, the glass bends the light.
Dark matter does the exact same thing to the light from background galaxies. By looking at how stretched and smeared out those distant galaxies appear, we can actually map out exactly where the invisible glass, the dark matter, is.
So we're like detectives looking for the invisible man by watching how the rain curves around his body.
That is a perfect way to put it. And we've made these incredible 3D maps of the cosmic scaffolding. And then the final piece of the puzzle is the cosmic microwave background, the CMB.
The baby picture of the universe.
The afterglow of the Big Bang. And the tiny temperature fluctuations in that light perfectly match a universe made of 5% normal matter and 27% dark matter. The math works. The observations work. The only question left is, what is this stuff?
Right. If it's not atoms, if it's not on the periodic table, what is it?
That is the multi-billion-dollar question. For decades, the leading candidate has been something called a WIMPy.
A WIMPy. Weakly interacting massive particle. Physicists love their acronyms.
They really do, and the name tells you what you need to know. Massive means it has weight, maybe 100 times heavier than a proton, and weakly interacting means it basically ignores normal matter.
So there are WIMPs passing through this studio right now.
Billions of them, every second. Pouring down through the roof, through your body, through the entire planet. They don't touch a thing. They're like neutrinos, but much, much heavier.
And we've been building these gigantic craps to try and catch one. This brings us to the latest news from the LZ experiment, LUX Zeppelin. Tell me about this thing. It sounds like something out of a sci-fi movie.
It really is an incredible piece of engineering. It's built a mile underground in an old gold mine in South Dakota.
Why so deep?
To get away from all the noise. On the surface, we're constantly being hit by cosmic rays from space. It would be like trying to hear a pin drop during a rock concert. The mile of solid rock above the detector filters all that out.
So it's completely silent down there.
That's the idea. And inside this giant cavern, they have a huge titanium tank filled with 10 tons of ultra-pure liquid xenon.
Xenon, like in fancy headlights.
It's the very same. They chill it until it's a liquid, and the whole idea is that just maybe one of the billions of WIMPs passing through might very, very rarely bump into the nucleus of a xenon atom. And that tiny little nudge would create a microscopic flash of light.
So they're sitting in a dark mine, a mile down, just waiting for a tiny spark. And in December of 2025, they released their big results. Did they find it? Did they catch the WIMP?
They did not.
All that work.
Silence from the mine.
That's disappointing.
Well, hang on. It's not a failure. This is really important. In this kind of physics, a non-detection is incredibly valuable data. The LZ results are the best in the world. They've ruled out a huge chunk of possibilities for what a WIMP could be. They've dramatically narrowed the places it could be hiding.
So they didn't find it, but they figured out where it isn't.
Exactly. And they did see something else, which proves the detector's working perfectly. They detected neutrinos coming directly from the nuclear fusion reactions happening in the core of the sun.
Wow. Okay, so the machine works.
The machine is exquisitely sensitive. It just hasn't seen the dark matter particle yet.
So if WIMPs are proving so elusive, what are the other suspects? Are we running out of ideas?
Not at all. The field is starting to pivot. As the space for WIMPs gets smaller and smaller, a lot of interest is shifting to another candidate. Axions.
Axions. Okay, these are the opposite of WIMPs, right? They're super light.
Ultra lightweight. If a WIMP is a bowling ball, an axion is like a fine mist, trillions of times lighter than an electron. The idea is they don't really act like particles that bump into things. They act more like a pervasive wave or a fluid that fills the universe.
How do you even begin to detect a mist?
With very, very strong magnets. The theory says that in a powerful magnetic field, an axion might, just might, transform into a photon, a particle of light. We're seeing all this new technology emerging to hunt for them, like at Texas A&M, where they're developing these cryogenic quantum sensors to listen for the tiniest whispers of these interactions.
It feels like we're closing in from all sides, but the net is still empty. And this brings up that idea of a crisis in cosmology. At what point do we stop looking for a ghost particle and start asking if our theory of gravity is just wrong?
And that is the counter-argument. It's a theory called Mon-ND modified Newtonian dynamics. The people who support it say, look, we've spent 40 years and billions of dollars hunting for a particle we can't find. Maybe there is no particle. Maybe gravity just works differently on the scale of a galaxy.
It's an attractive idea. It's cleaner, no invisible stuff.
It is. And MOND is actually really good at explaining those flat rotation curves from Vera Rubin. If you just tweak Newton's laws a little bit, the galaxies spin correctly without any dark matter at all.
So why isn't everyone a MOND believer?
Because it fails pretty much everywhere else. It can't explain the patterns in the cosmic microwave background. It can't explain what we see in gravitational lensing, especially in things like the bullet cluster, where we can literally see the dark matter separated from the normal matter after a collision.
So MOND fixes one problem but creates 10 more.
Precisely, which is why most astrophysicists still bet on the particle. But you're right, until we actually find that particle, the door for MOND remains open, just a crack.
Okay, so that's the glue, the scaffolding holding the cosmic mansion together. But now we have to talk about the thing that's actively trying to blow the mansion apart.
Dark energy.
And this is the really big slice of the pie, 68%.
The vast majority. And if you think dark matter is mysterious, dark energy is just bewildering.
So take us back to 1998. This is the moment everything changed. What were astronomers trying to figure out?
They were trying to measure the fate of the universe. Ever since the Big Bang, we knew the universe was expanding, but everyone assumed that gravity, from all that normal matter and all that dark matter, would be pulling everything back in. The expansion should be slowing down.
Like throwing a ball in the air, it goes up fast, but
Yeah.
gravity's constantly pulling on it, slowing it down.
Exactly. And the question was, is there enough gravity to eventually stop the expansion and make the universe collapse in a big crunch, or will it just slow down forever? And to figure that out, two different teams were looking at very distant time supernovae.
These are the famous standard candles.
That's right. They're a specific type of exploding star that always explodes with the exact same intrinsic brightness. So they're like 100-watt light bulbs scattered across the universe. If you see one that looks faint, you know it's really, really far away.
And they measured how far away they were and how fast they were moving away from us. What do they find?
They found something that made them think their equipment was broken. They checked for dust on the telescope lens. They reran all the software because the data showed that the most distant supernovae were even fainter than they should have been, which meant they were even farther away than predicted.
Which means the universe hadn't been slowing down.
No. It meant that for the last several billion years, the expansion of the universe has been speeding up.
The ball didn't slow down. It went up, and then it suddenly ignited a rocket engine and started accelerating away from us.
That was the jaw-on-the-floor moment for all of cosmology. Something is pushing space itself apart, overpowering the pull of all the gravity in the cosmos. And they gave that something a name: dark energy.
So if dark matter is the glue, dark energy is the pusher.
Absolutely. Dark matter clumps together under gravity, forming the scaffolding. Dark energy is perfectly smooth. It's a property of space itself. And as space expands, you get more space, which means you get more dark energy, which pushes harder, which makes space expand even faster. It's a runaway feedback loop.
So for a long time, the standard model for this was, well, it's kind of boring, wasn't it? We just called it a constant.
Yes. We called it the cosmological constant, or lambda. It's an idea that actually goes back to Einstein. He put it in his equations to keep the universe static before we knew it was expanding. When he found out it was, he called it his biggest blunder.
But it turns out he was right all along.
Ironically, yes. The idea was simple. Empty space just has an inherent energy, a certain amount of push, and it never changes. A cubic meter of space today has the same amount of dark energy as a cubic meter of space a billion years ago.
A steady foot on the accelerator, just cruising.
Exactly, and that idea, called the lambda CDM model, has been the standard model of cosmology for over 25 years. It fit the data really well. Until now, because this is where it gets really exciting. January 2026. The new data drops.
The bombshell arrived.
We're talking about two huge projects: the Dark Energy Spectroscopic Instrument, DSA, and the Dark Energy Survey, DES.
These are monumental efforts. DSI, for example, is this incredible machine on a telescope in Arizona. They fitted it with 5,000 tiny robotic arms.
Robotic arms.
Fiber optic positioners. Each one can pivot and lock onto a specific galaxies, so they can measure 5,000 galaxies at once. And every 20 minutes, the robots all reconfigure to stare at a new patch of 5,000 galaxies. They built the largest, most detailed 3D map of the universe in history.
And when they crunched the numbers from 6 years of this data, what did they find?
They found that the cosmological constant might not be constant.
Wait a second, so the energy of empty space itself has changed over time? The data strongly suggests that the density of dark energy is evolving, that over the last few billion years, it appears to have weakened. The data implies its density has decreased by maybe 10%.
The foot is coming off the gas pedal.
It looks like the foot might be easing up.
Okay, why is that such a huge deal? What does it matter if it's constant or changing?
Because if it changes, it completely shatters the standard model. It means dark energy isn't just some boring constant of nature. It means it's a dynamic field, something physicists have theorized about called quintessence.
Quintessence. Sounds like something from ancient alchemy.
The name comes from the fifth element, yeah. But in modern physics, it means dark energy is some kind of evolving field, sort of like the Higgs field, but for cosmic expansion. The analogy is a ball rolling slowly down a very long, shallow hill. It's not static, it can change, it's dynamic.
And that changes the answer to the ultimate question, doesn't it? The fate of the universe.
It changes everything. If dark energy is a constant, we get the big freeze. The universe expands forever. Galaxies get so far apart you can't see them. Stars burn out. Everything gets cold and dark and empty. A quiet, lonely death.
But if it's quintessence, if it's changing,
then all the options are back on the table.
let's run through them. What happens if it gets stronger, not weaker?
That's the scariest one. That's the big rip. If the repulsive force of dark energy grows, it will eventually overcome everything. First, it would rip galaxy clusters apart. Then it would rip galaxies apart.
Then solar system.
Yes, the Earth would be torn away from the sun. Then the Earth itself would be torn apart. And in the final fraction of a second, the force would become so strong, it would overcome the forces holding atoms together. It would rip you, me, everything apart at the atomic level.
Yikes. Okay. What if it gets weaker, like this new data hints?
If it weakens enough, gravity could eventually become dominant again. The expansion could slow, stop, and then reverse. The universe could start contracting, ending in a big crunch, everything crashing back together into a single point.
So we go from being shredded to being crushed. Great options.
Well, I should clarify. The current data from DAI and DAIS suggests a weakening, but probably not enough to cause a collapse. These new thawing models point to a middle ground.
A gentler ending.
It looks like the acceleration slows down, but the universe still expands forever. We probably still get a big freeze, but it's a much slower, gentler coast into the darkness, not a violent rip.
That feels slightly better, I guess.
It is less violent, but we have to be a little cautious. The statistical significance of this result is strong, what we call 3 to 4 sigma, but the gold standard in physics to claim a discovery is 5 sigma.
So translate that for us. What's the difference?
5 sigma means there's only a 1 in 3.5 million chance. The result is just a random fluke. We're not there yet. We're at the strong evidence, or this is really interesting stage.
Where there's smoke, there's a good chance there's fire stage.
A very good chance. But now we need to actually see the flames.
And to do that, we need even better tools. And we're entering a golden age for that, right?
We absolutely are. If you are a cosmologist, this is the most exciting time to be alive. We have the Euclid mission already up there, mapping the geometry of the dark universe.
And then there's the big one coming online. The Vera C. Rubin Observatory in Chile.
This is the game changer. I can't overstate it. Rubin is going to take a movie of the entire visible southern sky every few nights for 10 years.
A movie of the universe.
A 10-year time lapse. It will discover billions of new galaxies. The level of precision it will give us on dark energy will be an order of magnitude better than anything we have now. It will tell us definitively if dark energy is changing or not.
And we also have the Nancy Grace Roman Space Telescope coming up.
Exactly. Another space telescope designed specifically to hunt dark energy, to map the cosmos with incredible accuracy.
So all these new machines are designed to stress test our current model of the universe.
To try and break it. And there's one other crack that's already showing up, isn't there? The S8 tension.
Right. The universe is less clumpy than it should be.
In a nutshell, yes. When we look at the baby picture of the universe, the CMB, our standard model predicts exactly how lumpy and clustered the universe should be today. But when we look with our telescopes, the real universe is about 10% smoother than predicted.
Less clumpy.
It's another strong hint that our understanding is incomplete. Maybe dark energy interacts with dark matter in some weird way we haven't thought of. Maybe gravity is just a little different on cosmic scales. Something is missing from our equations.
It really feels like the standard model is just holding on by a thread.
It's under a lot of stress from a lot of different directions.
Oh.
We are finally detecting the ghosts that run the universe, and they are not behaving the way we expected them to.
You know, this brings up a huge philosophical question for me. We're always taught that the laws of physics are constant, immutable. But if dark energy, the single biggest component of the universe, can change over time,
if it can evolve,
does that mean the laws of physics themselves evolve? Was the universe a fundamentally different place with different rules billions of years ago?
And that is the really profound thought, isn't it? If the energy of the vacuum itself is not stable, then the very stage on which the play of reality is performed is changing. We might be living in a universe that is far more organic, far more dynamic than the simple clockwork machine we once imagined.
We might really be on the verge of a revolution in physics as big as the shift from Newton to Einstein.
I truly believe we are. We're finally looking at the 95% of the iceberg we ignored for all of history. And it turns out that iceberg is alive.
That's unbelievable. We started with a doorknob, and we ended up questioning the fundamental stability of reality itself.
That's cosmology for you.
So this means the story of the universe isn't over, the book isn't finished. We don't know the ending. In fact, the plot is twisting right now as we speak.
And it means that even the emptiness of space is filled with a dynamic, evolving energy we are just beginning to understand.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content released every day. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.